Okay, so today we're going to work on phase diagrams. Phase diagrams is where we're going to chart going from a solid, liquid to a gas. So before we start, let's look at our central question. How do I determine which formula to use when calculating the amount of energy is needed for a phase changes? So we're actually going to do some calculations later on. Before we can do that, let's get started with the basics. The basics is going to be solid, liquid, and gas. So I'm going to use this space up here, and I'm going to illustrate that. I'm going to illustrate a solid by drawing some particles, well, atoms, that be closely packed together, like so. Now these particles, they just don't sit there, they vibrate. They have a little movement. So I'm going to draw little vibrations around them, like little waves. They're always moving, just not moving much because they're really bound together. So this would be a solid. All right. Now a solid has a fixed volume. All right. Next one is going to be a liquid. Okay, I'm going to draw the little guys right here, the molecules. Now this one, since you can't just have liquid sitting on a counter, we're going to put like in a little cup. All right. Cup, here's our little particles. Again, they're going to vibrate too, but this time they're going to get a little bit more movement. Put a little 3 on there. You get a little bit more, but not much. This time they have a fixed volume, but not a fixed shape. So solid, which is fixed volume, fixed shape. Liquid, fixed volume, not a fixed shape. But this time the particle is able to move around a little bit more. The next one is going to be gas. I'm going to draw a little vessel here. Really, we could put one on the solid one too. Why not? Make them all the same. All right. This time on this vessel, we have a gas, the particles. I'm going to put 3 on here. Okay. In this case, there's going to be even more movement. They bounce around really quickly. In this case, they don't have a fixed volume or a fixed shape. And this is a gas. Now, to see what this actually looks like, let's actually go to a PhET simulation. Oh, no, wrong thing. Let's go right there. Okay. So here's a PhET simulation. We have here a whole bunch of different particles. In this case, it's neon particles. Now, right now, they're close together and they're packed. This would be a solid, right? Here's a solid. They're close together and packed. Notice there's a little bit of movement going on. Not much, but there's still some. Now let's add energy to it, right? As you add energy, you notice it start bouncing around a little bit more, right? We're going to basically melt it and turn it into a liquid. Now we're turning to a liquid here. It's bouncing around a little bit more. Now what happens if we keep on heating up even more? What are we going to have? All right, it's going to start turning to a gaseous state. Let's turn that to Celsius. All right, it's going to be more gaseous, going to be going around everywhere. Notice there's more movement, more kinetic energy. Now let's try this again. Let's try it with water. All right, so this would be like your ice, an ice cube. Now they're all close together. There's a little bit of movement, but not much. Now let's add some energy to it. Add energy. The molecules are increasing in kinetic energy. There's more movement. So now it's liquid. We know it's liquid because look here at the temperature. Between 0 and 100 degrees Celsius is liquid state for water. So they're still moving around. Now we keep on heating it up to past 100 degrees Celsius. We should see it turn to a gas. See what's going to happen to them. There you go. We got a lot of kinetic energy going on. This is basically it's boiling right now. It's boiling. Now I see them flying around. The kinetic energy is really high with these molecules. So we have a gaseous state. So we have a solid, close together, a little vibration, liquid, they're able to move around a lot more, and a gas. They're having fun. All right. That looks fantastic. Okay, let's go back to this. Now, before we can get started with a phase diagram, we need to go over some vocabulary first. Some of this vocabulary might seem really simple, but it's going to help you if you go ahead and get prepped for it, right? Meow. All right. So we have melting. I want you to illustrate what you think melting would be like. What would it show? I'll give you an example for the first one. The other ones you have to do your own. So we have melting. I would think it would be like an ice cube. That's basically going from solid to liquid, right? Be like an ice cube like this, turning into liquid. Just for fun, just add a little blue there. There we go. Now for boiling, gotta try to think, what would boiling be? Think of like ramen noodles. Draw an illustration for your boiling right there. Now for vaporization, this part I'll help you with. What is vaporization? So think of boiling when the water is turned from liquid to gas. So I'm going to draw me a little pot that I would have on my stove. So does that be pretty? I'm going to put a little bit of water in there. For my blue pen, I lost my blue pen. Got some water. I'm going to form some bubbles. So those bubbles are going to come to the top of the water. They're going to basically pop, and you're going to have that gas coming up. So I'm going to put a little vapor. It's basically from a liquid to a gas. The next item is condensation. This one you're going to draw, but I'll verbalize what it would look like. Think of it's summertime. You can go to the fridge and get a glass of ice cold tea. You go outside and you set that tea out in the sun, on a bench or whatever. You notice outside it starts getting wet. Now that stuff on the outside of the glass is not the tea, but water. So what is that? Cold tea is making the gas outside in the air condense and form into a liquid. So go from gas to liquid. Or think of it as a soda. You get a soda bottle, you put it in the fridge a little bit, you bring it outside, it starts getting wet on the outside of it. Now the soda's still sealed, but how is that liquid getting there? It's taking that gas from the air and condensing it and making it to liquid. So cold. So I want you to draw that right there. The next two, we're not doing these yet. We're going to come back to this when we revise our notes. So hold off on these two. Great. Now what we're going to do is we're going to make a chart. We're going to graph phase changes from solid, liquid to gas. So what would that look like? Well, first off, we need to do our X and Y axis. On the X axis, we're going to put energy. And it's going to increase as we go to the right. On the Y axis, we're going to do temperature. Right, I'm going to do it in degrees C. It's going to increase as we go up. Okay, then you need to make a little mark about right here and right here. This first mark is going to be for the melting point. So I'm going to put an MP. And the next one here is going to be for the boiling point, or BP. Okay, now before we move on, I'm sure some of y'all are probably thinking of this, but isn't energy and temperature the same thing? They are not. So what you need to do is think of energy as the movement and everything, basically joules, heat added. Temperature, what you want to think of is how fast the particles are moving. Think of it as the kinetic energy of the particles. So if we go back to the PhET simulation, we see the particles have a lot of kinetic energy. The temperature is going to be higher. The lower kinetic energy, the temperature is going to be lower. Think temperature as the kinetic energy of the particles. Okay, so I'm going to put a lab on the top right-hand corner of this, so I get to play here. So we're going to do a lab up here in the top right. It's going to be playing. This is going to basically take ice we're going to melt it to liquid and to gas. So if you're in person, we're going to be doing this in class. If you're remote, you get to watch this part of the video. Or if you're not able to do the labs because of safety ordeal, or you didn't bring contract signed, or you did something that's totally unsafe, you can't do labs anymore, this is what you got. All right, so we have here is a hot plate. We have a beaker filled with ice, a CPO monitor, which is going to measure the temperature and time. Okay, so we're putting this thermistor in the water. We're going to heat up the hot plate. And we're going to basically, when we get this, it's going to be charting the actual melting of the ice for different phases. I'm actually going to speed up just a little bit so we can get a little bit started here. There we go. So we have here the hot plate is on, it's heating up that water, and there is the graph starting right there. All right, so let's go and start. So we're going to start off in the bottom left here, and I'm going to make a little dot right here. And we're basically have a solid. When something is a solid, right, and we're trying to heat it up like ice, take an ice cube, when we heat it up, it's not going to start melting until it gets about 0 degrees Celsius or 32 degrees Fahrenheit. Everything below that, it will still be ice. Say if we're negative 20 degrees, it's going to stay solid. You keep on heating it up until that 32 degrees. Or say you're negative 20 degrees Celsius, 0 degrees Celsius. So as we increase heat, it's still going to be solid, right? Until it hits its melting point. So this would be a solid. And you'll be able to see this in a moment on the graph. Right, so we have solid right here. Now, once it hits the melting point, it's going to start going from solid to liquid. When it does this, it's going to be a horizontal line. And it's just going to melt. So I have a diagram here from a previous one. Ignore this part right here. That's where I took the thermometer out. If I cover this part here, you can see this flat line right here. That is the point where the ice is melting. It's melting. So once it's past this melting point, it's going to stay a liquid. It's going to stay liquid all the way to the boiling point. Right? So this is going to be a liquid right here. So I look at this graph, ignoring that other jump. You can see this angled right here, this line, diagonal line. That right there is where it was liquid. So keep on going until it's liquid, until it starts boiling. Let me see if I can go ahead and get this video, this lab portion up here, where it starts, see, starting liquid up there. Melting, melting, all liquid. Okay, now we get to the point where it starts boiling. Right there. It's hard to see, but if you look close to that beaker, see little bubbles popping right there. Not many of them, it's a little bit. And it's in the graph, it's starting, it was going at an angle, and it's starting to plateau off. Move it up just a little bit more, so you can see that plateau. Starting to plateau off right there. There we go. See the boiling right there going on? It's not much, it's very little. The water is very dirty. There we go. Now see this chart? It's going to go off an angle, it's starting to flatten off. There we go. So that flattening off is where it's going to, the liquid is going to start trying to turn into gas. Right, and this is called a vaporization. Now, when that liquid does turn to gas, I'm sorry, you couldn't see that there. Drew a horizontal line for vaporization. Right, now when that liquid does turn to gas, it's going to just keep increasing its temperature right there. And this would be our gas. We start from solid, we start melting, liquid, starts vaporizing, or same thing as boiling, and turning to a gas. So the energy is going to increase as we go up. Okay. That's going to solid to gas. What about from gas to a liquid? Think of it as if you're trying to make some ice pops or something and you put it in the freezer. So we start off with some water. You put that water, it could be just, actually let's go back. Let's say we have gas. We start gas as it loses temperature, it starts condensing. Think of the gas outside your soda. It starts condensing, goes from liquid to gas. I just misspelled right there. So condensation. It starts losing energy right there. Gas to liquid is forming outside the bottle. If we take that liquid and we put it in the freezer, until it gets to 32 degrees, it's going to start, it means liquid, until it's 32 degrees. Once it's 32 degrees, it'll start freezing and losing temperature that way. So gas is condensing, going from gas to a liquid. Then you see it getting colder, it's going to go liquid to a solid by forming ice. Great. All right, let's get to the fun stuff of actually doing calculations. Probably saying yay. All right, we just went over the phase diagram where we increase energy. We go from solid, liquid to gas. We do this for the phase changes of going from freezing or melting and vaporization or condensation. All right, so I know this will be hard here to see. Hopefully yours is better, but this is for water. We're going to calculate the energy needed to change phases or change temperature. We have two charts here. What you right now is draw a line between these charts. On the left-hand side, we're going to put temperature. And on the right-hand side, we're going to do phase. All right, so to calculate how much energy we need to change the temperature or phase, we're going to use two different formulas, or actually three formulas, but two different sets. And first off with the energy needed to change temperature. We're going to use the formula Q equals MC A T. Q equals MCAT. I always say an A, it helps me remember it. All right, so Q stands for the energy. That's Q. M is going to stand for your mass, like you mass your substance. Like when we did the thing with the water boiling, it's like how much water do you have? How much is the mass? The next one's C. This is going to be something new. This is called specific heat. It's represented by C. What the specific heat is, it's a value that we use. Basically, it's how much heat is required to raise the temperature of the 1 kilogram of mass by 1 degree. Let's say if we have for water, it's a certain value we needed to find out for the water to increase the temperature by 1 degree, given the amount of, on the mass, like 1 kilogram. You always be given these values, so don't stress it. But it is a property of all matter. All matter has this property. Just what the number is different. You always be given a chart though. In this case, if we're doing here with liquid, water, ice, or I say liquid, water, ice, gas, which is steam, water, or ice. So gas, liquid, solid. I don't know what I'm thinking. And the next one is your delta T. A delta, it means a change. So a change in temperature. And this is always your final minus your initial. All right, change in temperature. And we'll do a couple of these walking through, not a problem. So this, I have these diagrams. I want you to mark these. You get a different colored pen if you got it. For change of temperature, and we're still the same phase, will be items in this area right here. It's just changing temperature. We're still solid. Our liquid here, we're still liquid, same thing. And gas. Only when the chart is in these sections here, we use the formula energy equals mass multiplied by specific heat multiplied by the change in temperature. This is only three places you would use this formula. For the other one over here, we have two different formulas, but don't stress it out. Remember, these will be given to you for now. It's going to be these areas right here. It's where we're changing phases. All right. The first formula is going to be Q. Let me change the colors here. Q, which is your energy, equals your mass multiply the delta H fusion. That's when we go from solid to liquid. Q equals M delta H fusion. Again, this is me given up here. Mine's hard to see it. You'll be given these values. That's where you use that value. Again, we're going to walk through these, so don't stress it out yet. We're just going over the formulas. The next one is going to be Q equals M, which is free mass, delta H vaporization. So for fusion, that's going to go right here. That's this section right there. For vaporization, it's going to go right here. So help, like fusing is like when you're binding things together. Think of it as like freezing, fusion. So one would help remember that. And vapor, vaporization. That's where you like boiling and cooking your noodles and such. All right, so let's actually do a practice one of these. All right, so you can turn over your sheet. I just happen to have one right here. And let's do a practice problem. And a couple of these so we get used to doing it. Now, I'm going to help you with each of these ones right here. You're going to have your own class kit to do your own practice with. These are the ones you're going to see basically walk through. First one is, how much energy will it take to get 25 kilograms of ice from negative 30 degrees, I should say C, Celsius to negative 10 degrees Celsius? So I'm going to change in temperature. So we're taking ice. So we're going to use this formula right here. Q equals M specific heat delta T. So we're going to try to find how much energy. This is what we're looking for. It's asking for how much energy. Now let's look at the values. We're given 25 kilograms of ice, 25 grams. So this will be our mass. Now we need to find here our temperature. We're going from negative 30 to 10 degrees. So we know that's going to be a change in 20 degrees. All right, that's 20 degrees Celsius change from 30 to 30 to 10. All right, let's go ahead and plug it on in. Change what's in here. So Q equals, I'm going to take my mass of 25 grams, multiply it by the specific heat, which I'm going to use my chart. Always go to my chart. All right, and we're going to deal with ice here. Ice, what? 2.09 to 2.09. And we multiply it by our delta T, our change in temperature. And we have negative 30 negative 30 to negative 10. So we have a change of 20 degrees. Awesome. Now I'll let you go and get Desmos and do your own values there. Let's do the next one here. How much energy will it take to get 10 grams of water from 12 degrees to 17 degrees Celsius? So again, we're just doing it with water. We're not changing the phase or anything. We're just going from 12 degrees to 17 degrees. So we use Q equals MCAT, mass, specific heat, delta T. Again, we are looking for how much energy, so we're just solving for Q. We're given a mass of 10 grams, so that's our mass. We're done with water. Our change in temperature is right here. All right, let's go and plug it on in. Q equals our mass of 10. We're doing with water. We gotta find the specific heat of water. So looking up here, it's 4.18. And now we have to find our change in temperature. Remember, change in temperature is final minus initial. So last time I didn't write it down. This time I will, just so in case someone got lost. 17 minus 12. Remember, that's our final minus initial. Okay, now you pop that in your handy dandy calculator. But that's some work. I'll let you do that. Let's go to the next one. how much energy will be lost to get 31 grams of steam from 115 degrees Celsius to 105 degrees Celsius? Okay, so again, it's asking us for how much energy. So we'll be solving for Q. So lost, if we're losing, that might be a hint, just maybe, we might get a negative symbol or negative value at the end. Just a hint, maybe. We have 31 grams. This will be our mass. And we went from 115 degrees to 105. So again, this is our temperature. Let's write down our formula. Q equals M specific heat delta T. Okay. Now, since we're doing with steam, we know we're going to use this value right here, 2.01. Let's write that real quick. All right, so Q equals the mass of 31, our specific heat, which is 2.01, and our delta T, which is our final minus our initial. All right, so our final, which is 105 minus our initial of 115. Okay, remember, it's talking about loss, that's backwards, so we probably get a negative value here. That's all right. All right, so I'll let you pop that in your handy dandy calculator and solve it. Let's move on. We got 2 more to go. Next one is, how much energy is required to melt 75 grams of ice? Okay, how much energy? But now we see the word melt. Okay, ooh, that's the difference here, melt. And also, we don't see temperatures here. We don't see a final or initial. So that's also key that we might not be using this formula here, but probably one of these. We saw the word melt. So you might want to write that here too in the next part. On the previous page, if we see the word melt or freeze or boil or condense, those may be clues for me using one of these. Okay, let's write down our formula. Q equals what? So we got melting. Looking at our diagram here, melting is we go from solid to liquid. So we have two sections we could use. This goes from liquid to gas. So that would be a vaporization. We have a solid to liquid. So this will be melting right here. So this is the one we'll use, which is Q equals M, your mass, the change in heat fusion. So let's go and put M, Q, H, fusion. Great. Let's go ahead and plug in our values. If Q equals our mass, which I did not mark right here, but I should have. Okay. Our mass, which is 75 grams, multiplied by the unit for, the value for heat fusion. So I'll go look at my chart that I'm given, and I see it right here, 333 joules per gram. Now for right now, I'm just going to do it without the units, but we will do those later on. Right now we're just getting started off without it. Tomorrow we'll start plugging in the units. Okay. Now this part I'm sure you can do. I'll let you do that with your own math. You are all in algebra and geometry. I'm not showing you the math part. You have that. Okay, let's go to the next one, and the last one here. It is how much energy will be lost when 32 grams of steam condenses? So again, it's asking for how much energy. Okay, be lost. So we might have a negative, maybe, maybe not. We have 32 grams, which is our mass of steam when it condenses. Condenses is going to be a hint word that we're using one of these. Okay. Let's start off by writing our formula. You know it's Q equals what? Since we're going to be condensing, we're using one of these two. When you go solid to liquid, we are basically melting or freezing. So that's not this one. If we have a liquid to gas, we're either going to be vaporizing or condensing. Well, we're looking for condensing, so this will be the section we need. So we'll be using Q equals M delta H vaporization. So mass delta H vaporization. Let's plug in our values, shall we? Q equals our mass of 32. And this value we can find up here, which would be 2,260 joules per gram. And right now, I'm not going to put the unit on. We'll start doing that tomorrow. Right now, just get the basic premise of it. We'll leave the unit off. Awesome. Now, I'll let you do that math real quick. Again, I'm not going to do it. I'm sure you all can do that. You're in algebra and geometry. You are golden. Okay. So we have left right now is these three questions. We have three formulas. Q equals MCAT. Q equals M delta H fusion. And Q equals M delta H vaporization. My question to you is, when are these used? Think of these problems and the information we have in our notes right here, and write down when do you know to use which formula. So when we did these formulas right here, what gave us a hint that we need to use this one? When we looked at this question here, what gave us the hint that we need to use this one? When we use this question, what gave us the hint we need to use this one? Remember, use the information here on your practice problems, then also area in this diagram to help you out. Okay. For the essential question or the summary, you're not filling this out now. You'll do this tomorrow when we get into class. So once you finish the sets of notes, what we're going to do now is go to ClassKick. The code is in Canvas. And we start doing our practice problems with these right here. Okay. Thank you.